So now let's take a look at the custom feature that I've been mentioning that I built for the Nexus 9K for a customer in order to solve a problem that they had, and specifically one that had occurred with their IPS intrusion protection system bypass mechanism. And I used Python and EEM to solve this issue. So the problem essentially was that they had their internet connection where all of their really revenue-driving traffic came from. And this was a large financial institution, and lost packets or lost dropped traffic had cost them many millions of dollars just on 9 minutes of dropped traffic was what they had experienced. So essentially, they had traffic coming in, and as it was coming in through their switch from the internet, hitting their SSL decryptor, and then going through their SourceFire next-gen IPS, they had an issue where their SSL decryptor essentially stopped passing traffic. And they also wanted, just in case, let's say the SourceFire stopped passing traffic or any sort of IPS, they wanted there to be some sort of a bypass mechanism. So at this point, there's a loss in traffic that ended up costing them millions of dollars. Now, the decryptor should have gone ahead and failed to wire, meaning that it just passes traffic through even without decrypting it, and the SourceFire may not have been able to inspect it properly, but at least it would have gotten on to its final destination. Because essentially what happens is this traffic comes in, gets decrypted, the IPS, the next-gen IPS inspects and blocks any bad stuff, but then passes it back to the SSL for re-encryption before it traverses the corporate network and it gets to the ultimate SSL decryptor where it gets to the web servers or the application servers. But in this case, the SSL decryptor not allowing it to pass through, and they wanted the potential of, if the IPS had caused that as well, they wanted that to go ahead and trigger this. Or they gave us another requirement, which wasn't even based on something they had seen, but just something they wanted, which was that if the latency of these devices was too high, if it exceeded a certain threshold, a user-defined threshold, they wanted this traffic to bypass. So our solution was this IP bypass. Now we were using essentially spine leaf architecture with Nexus 9000 in standalone VXLAN with EVPN control plane. And so this 9500A and the internet could have come over to another, there was obviously going to be redundant switches. And actually, that was another requirement, was they not only wanted the redundant switches to be able to both pass traffic and active-active, but they wanted these processes, these features of essentially this health check, this net health check that I created, they wanted it to run independently on each device. So if one of those processes died, they didn't want it run on like a third-party central server where they had to maintain a new server or a new pair of clustered servers for additional management on their network. They wanted to run on box, and they wanted each of the Nexus 9Ks that were allowing traffic to come in from the internet to both be running the process independently. So essentially, here's what we did. By the way, it's probably worth noting that in the previous example, this is all one layer 2 construct. So traffic coming in from the internet is on, let's say, VLAN 10. It goes out VLAN 10, it comes in on a particular port. It goes out on a particular port, both VLAN 10, passes through to the SSL decryptor, gets decrypted, passes through. These are transparent devices. So SourceFire next-gen IPS is in transparent mode, passes it back to the SSL re-encrypt, and then back onto the corporate network. So here we have E1 and E2 that are both on VLAN 10. And these are still transparent devices, but now we're passing them, instead of through the decryptor, through the SourceFire next-gen IPS, back to the SSL encryptor, and then back directly to the network, we're passing it back onto the same switch. Now, if the E3 and E4 were part of the same VLAN, then the MAC addresses that were learned from 9500B and the rest of the network would have simply been learnt on VLAN 10, on E4, and E1 would have simply sent the traffic direct. So what we did was we placed E3 and 4 in a separate VLAN, and essentially the only way, the MAC addresses, let's say MAC H that's out here, the only way MAC H is learned is on E4 on VLAN 11, And so in order for, an internet device for that traffic to come in on E1 on VLAN 10 and pass to MAC address H, well, it's learned through this interface here because of the transparent device. So this transparent, or pair of transparent devices in this case, is what's allowing this MAC H to be learned on E4, passed down through E3, and essentially learned in through E2 on VLAN 10. So that's how the switch, when it gets the packet or frame in from E1, it knows how to pass it on to MAC address H, is to go through E2 on VLAN 10. So the traffic comes in and it essentially passes through. And notice we have our internet traffic, and then we also have a health packet that I'm creating, and this is a Python script that's doing an ICMP ping. Now, how is it doing an ICMP ping? Because I have an SVI. So I have an SVI for VLAN 10 and an SVI for VLAN 11. So SVI for VLAN 10 is essentially, let's say 10.1.1.1, and the interface VLAN 11 is 10.1.1.2, both /24. They could be, /30 to be a little more, whatever. But the idea is, and that would be a little more scalable, so that's great. We could use /31s as well. So the idea is, you might say, well, wait a minute, I can't have two overlapping IPs, or they're not really overlapping IPs, but overlapping IP ranges on two different SVIs. How are we going to know where to route 10.1.1.0/24 traffic? Well, the traffic from VLAN 10 SVI and the traffic or the IP address on interface VLAN 11 SVI, they're on different VRFs. So because they're on different VRFs, the only way that we'll learn about, and also I should note that with Nexus 9K, we have the ability to change the MAC address. So they do have to be different MAC addresses as well. So we have a custom MAC address. So the only way that we're learning about the MAC address from SVI VLAN 11 from SVI VLAN 10 is through E2, again through this transparent L2. Okay? So when I source an ICMP packet from VLAN 10 and I have that go through this device, then, essentially when I source a packet, I do an ARP, and I learn that the MAC address for SVI VLAN 11 is coming in through E2 because I didn't do any VRF route leaking on box, so there's no way for those two to communicate other than through that transparent device. So essentially VLAN 10 and VLAN 11 and the two SVIs are all one broadcast domain, even though they're separate VLANs. So for instance, I can, after I save my running config, I can go ahead and just enable guest shell from exec level. And then from there, from within the guest shell, I can see that I have a sudo bash shell here. I can cd to a particular directory /boot flash, and then I could, get into using vi or vim, and maybe I don't have vim installed, so I can do a yum install on vim, but I can have, sudo access and really root level access to that configuration, and then I could modify that config, and that's obviously just a very small example. So let's look at some hands-on with the guest shell. First of all, from a Nexus 9K, I can look at, or 3K, I can look at show virtual service list, and I'll see that the guest shell should be activated, and the package is the OVA that was used to install it. I can, from exec mode, drop down into the guest shell, print working directory, use all my standard Linux commands. Whenever I want, I can exit back out into the NXOS. Now, by default, communication is performed using the default VRF. However, just like I can chown, chgroup to change ownership or change group membership, I can chvrf, right? So I can change the VRF, which is a custom tool that Cisco wrote to allow me to choose which VRF I want to interact with. And then I could do, for instance, change VRF to management and issue a ping from the guest shell. Otherwise, it's just going to be using the default VRF. Also, I have the ability to do host. So this is a tool that Cisco wrote that essentially runs on the underlying host, and it allows me to do a particular command on the host, even though I'm in a Linux container, a guest shell. So I could basically, instead of saying do show version, I can do that on the host. So I can do show version on the host, or do host show version pipe to include chassis. Okay? And then that will return the output here to the local guest shell. And note that it returns code and output for each command passed. And I can actually do multiple commands. So config t, cdp timer 10, line console, exec timeout 0. So running guest shell commands from the host OS, let's say I'm in guest shell and I pwd. From the host, I can actually, instead of just saying guest shell enter, I can say guest shell and then issue the command that would run in the guest shell. And then this would, pass me back the working directory, list the files, and I can, for instance, call guest shell space python space hello pi, because I know where I am and what files happen to be there. And if not, I could issue the full, absolute path, guest shell python /home /guest shell /hello.py. So again, I can use this to schedule commands in the guest shell. So for instance, I'm here in the host mode and I'm in config t, global config, and I run feature scheduler, and then I run, this is essentially a cron job, and I run schedule job name, and I give it a name, and then I define what is running in that job. So guest shell python hello.py end, and if I show the scheduler, I'll see what that is, and then I can basically specify when to kick that off, daily at 2 a.m., or start now and repeat at 2 a.m., and I can show the scheduler log file. Likewise, I can interact with the guest shell with EEM, as I mentioned. So I can do feature EEM and enable the enhanced event detectors. And I could, for instance, say my event manager applet test, when CLI matches, when someone runs show version, automatically kick off the CLI for guest shell python EEM.py. And in this case, show version basically blocks one particular command by event manager policy. So something is actually being blocked to customize, role-based access control, but even more granularly. So we also have package manager, or RPM. So we have the ability to install packages via yum. So I can drop down into the guest shell and then do a sudo to, super user do, or do as the super user, or do it as root, to change VRF to management and do a yum install of a particular application like Bison. So from there, Bison is installed, and once it is, it's processing dependencies as well, and assuming those dependencies are resolved, then it's basically saying it's going to install 4.6 meg of file. Is this okay? And I issue yes, and it will go ahead and install this application. I can also do pip, so the Python package manager. Okay, so from here I can install packages. I could do a pip freeze to see what packages I have installed and what versions, and I've got full Python capabilities there. Now Python 2.7 is installed and prepackaged. Most people are still running 2.7 even though 3.x is out just because of major changes. We've talked about that already. So Python 2.7.3 specifically is what's running. And we can either do the interactive shell, as we talked about, or create a script file, upload it through FTP, SFTP, or just create it right there on Box with Vim. And then of course we can run this. So we can, here we're creating or editing a file directly from the host, not from in guest shell, but running guest shell and then VI to create boot flash scripts, find vir.py, and then we're actually executing that and running it. So for instance, here's just kind of a sample program that is here to create a socket and send data and bind to a particular socket stream and listen for data. So we can even use Python sockets. So let's say we have a problem definition, which is that device configurations aren't easily tracked. Once a configuration change is committed, it's difficult to recover the previous state. So config management systems are often proprietary and costly, but we could use, let's just say EEM to track when copy run start is issued, and call a Python script that commits that configuration to a Git repository, either a proprietary, or I shouldn't say proprietary, but a downloaded and installed running on your own environment Git repository, or even GitHub in a private repository. You probably wouldn't want it out there in GitHub, the free version, but when you pay for a few bucks a month, you can actually have your own private repositories. So this would give you cloud-based backup and storage of all your configuration, secured, encrypted, and all of your switches are automatically backing up not only their configurations, but not nightly, weekly, hourly, but only when there's a change made, only when there's a delta. And using get, we can clearly see in red lines that were deleted and green lines that were added when we compare one config file versus another historical revision or config file. So the implementation, we'd split it into two parts. We'd have EEM to trigger the write mem, basically when someone did a copy run start or a WR for write, and then the Python script would do a git add or commit or push it to the repository. So for instance, part one for EEM, we'd match copy running config to startup config or any variation thereof, and we would do a CLI copy running boot flash, and then wherever we had stored it to, I saw Sturgis, and yeah, anyhow, to a particular file, and then do a guest shell sudo, and we'd basically run our Python script, and then our Python script is going to do an OS and pop open that file or open that file, and then it's going to do a file read, it's going to do a close, and print the result, basically who had made this change. And then we're going to do a, actually this is just CDing to the directory, and then, here we go. So in boot flash, we're doing a git add running. Okay, so we're going to go ahead and commit that to Git. And then in our Git server, and this is just one running locally, it could be GitHub. We'd put a little more logic in there for that. We could quite easily see any changes, right? So again, we have our red is our delete, our green is our additions. So we can see that the line for time has been deleted and a new line has been added, which makes sense because it's going to be a completely different line. We can see that CDP timer has changed from 20 to 30, and that a brand new interface has been brought up when we're looking at one version or revision versus another.